Okay, in this video we'll take a look at how to, given an original graph, sketch the derivative graph. And I want to emphasize here, sketch the derivative graph, not make a detailed graph. And we'll talk about that in just a second. Now to begin with, let's take a look at a pretty simple example here. Suppose you had this, y is equal to x squared, and the curve is a parabola that looks like this. Now what we'll do is the original graph will be on top. We'll sketch the derivative graph down here on the bottom. Now, the derivative gives you the slope of the tangent line at any point on the original graph. So if we were going to do this thing point by point, now in general we won't do it this way, but on this first one we'll do them point by point. So what I'm going to do is this. So I'll come over here to where x is equal to a negative 2, and I'll go straight up to the graph, and here's a point on the graph right here. Now if I were to draw a tangent line to that point, that tangent line would look something like this right here. Now, the slope of that tangent line, if you found rise over run, you would find out to be a negative 4. So the slope of this tangent line is a negative 4, and we'll show where that comes from a little bit later in this video. Now, to actually have some points to plot, when x is equal to a negative 2, the slope is equal to a negative 4. So it comes straight down from that point down to here. So where x is equal to a negative 2, y is equal to a negative 4, and plot you a point right there. So that takes care of the slope at this point. And we'll just continue to work our way around the curve. So let's go to where x is equal to a negative 1. So here's a point on the graph. The slope of it, I'll first of all draw a tangent line. The tangent line would look like this right here. Now the slope of this tangent line is a negative 2. It's still negative. So when x is equal to a negative 1, from that point come straight down. Here's negative 1, and let y equal to negative 2, and I'll plot a point right there at negative 2. And we'll continue to work our way around. So now we'll go to where x is equal to 0. Now in this case you have a horizontal tangent. So the tangent line at that point right there would be horizontal. The slope of a horizontal line is 0, so the slope of that line is 0. So I'll come down where x is equal to 0, and I'll plot a point at 0. So all you're doing on this graph down here is just plotting the slopes. Negative 4, negative 2, 0. Now let's go where x is equal to 1. So there's the point right there. I'll draw the tangent line, and the slope of that tangent line is 2. So I'll come straight down from from 1 and plot a point right here at 2. And then finally let's do one more. When x is equal to 2, we'll go up to the original function. There's the point. I'll draw a tangent line to that point, and the slope of that tangent line is 4. So I'll come straight down from 2, and when y is equal to 4, I'll plot a point right there. So what I've got on this thing is, here are the x values on the x-axis, and on the y-axis, each one of these points represents the slope of the tangent line at that given point. Now, if you were to connect all these points, you would have something that looks like this. Let's just draw a line here. So you'd have a line that goes straight through here like this. And that is the derivative graph. That's the graph of y prime. And that's how you do it point by point. Now, just to give you another way of looking at this, suppose we decided to take the derivative of this thing. Then y prime, let's find the derivative of this. So if y is equal to x squared, then y prime, the derivative, would be equal to 2x. So here's a function 2x. Now you can build a table up and actually plot some values. Let's do it that way. So if I were to come down here, and what I'm going to do is just put some values in here. I'm going to use the same ones I did before. Negative 2, negative 1, 0, 1, and 2. So if you were to take negative 2 and plug it into this, you'd have 2 times a negative 2, which would give you a negative 4. The slope would be negative 4, and that's where this comes from right here. So you plot the point at negative 4, we'll kind of put a little circle around. There's the first one. If you plugged in a negative 1 into the derivative function, you'd have a negative 2. That's that slope right there. So you plot that point, and it would be right here. If you plugged in a 0, then you'd have a 0. That's this slope right here. It'll give you that point right there. If you plug a 1 into the derivative function, you'd have 2, and that will give you that slope right there. This one would be 2. And then finally, if you plugged a 2 into the derivative function, you'd have 2 times 2, which would be 4, and that will give you that slope right there, which is 4. And then if you connected the line, you'd have it. Now also just think about it. If you just graph the line y is equal to 2x, that's a straight line that goes through the origin with a slope of 2, and that's where the derivative graph comes from. So if this is the original function, this is what the derivative graph is going to look like. Now before we go on, let's take a look at a couple of variations on this one. What we're going to look at, we looked at the first time, y is equal to x squared. Now the only difference between these three graphs, this one is going to be y is equal to x squared plus 1. This one's going to be y is equal to x squared minus 3. So the graphs will have the same shape, except this one has been shifted up by 1. This one has been shifted down by 3. And I get some students think that, well, since it's a different graph, surely it's going to have a different derivative graph, but not necessarily, and let's kind of watch this. What I'm going to do is repeat exactly the same process I did on those other ones. At -2, I'll come up to here, and I'll draw a tangent line. The slope of that tangent line is -4. I'll come straight down from here and plot a point at -4. I'll go to -1. The slope here is -2. I'll come straight down from here, plot a point at -2. Horizontal tangent right here at 0. The slope there would be 0. I'll plot a point right there. I'll go to x is equal to 1. Draw a tangent line. The slope of that tangent line is 2, so I'll plot a point at 2. And then finally, when x is equal to 2, there's a tangent line there. The slope of that tangent line is 4, so I'll come when x is equal to 2, I get 4. And if I were to draw this line, you'll see that I get exactly the same line that I had in that last graph. So the point that I want to make here is that even though the graphs have been shifted vertically, they have exactly the same derivative graph. That was going to be the graph of the derivative. So just remember that the graph of the derivative is based on the slope of the tangent line at any point. And on this one, if you were to do the same thing, if you were to go to -2, we'll kind of run across here, -2, then the slope here would be a -4, and you'd get exactly the same graph. So at -2, you'd have -4. The slope right here would be -2. The slope right here would be 0. The slope at 1 would be 2, and you'd have a point right there. And finally, the slope at 2, if you went up, the slope right there of that tangent line would be 4, and you'd have this. So if you drew that graph, it would look like this also. So all three of those have the same derivative. Now, it'll make sense when you take the derivative of this. If the original function was y is equal to x squared, the derivative is y is equal to 2x. If the original function was x squared plus 1, then again, the derivative is still 2x because the derivative of a constant goes to 0. So it has the same derivative. And same thing over here. The derivative of this one, y prime, would be equal to 2x because the derivative of a constant goes to 0. So since all of these have the same derivative, they all have the same derivative graph. Now, that's the only one that we're really going to do in detail. What we generally want is the slope. And the important thing to take away from this thing is this, is wherever you have a horizontal tangent, right here, then the slope of a horizontal line is 0. So the derivative graph will cross the x-axis, it'll go through 0. Now, in this interval right here, each of these slopes was negative. So since the slope of the original function is negative, then the graph of the derivative is going to be below the x-axis. It's going to be negative. In this interval over here, all of these slopes were positive. So since the derivative gives you the slope of the tangent line, in this interval, the derivative graph is going to be above the x-axis and it'll be positive. So just remember, if you have a horizontal tangent, the graph of the derivative crosses the x-axis. If the original function has a negative slope, the graph of the derivative is below the x-axis. And finally, if you have a positive slope, then the graph of the derivative is above the x-axis. So with those in mind, now we'll take a look at a few just general problems and see what they look like. And we'll just kind of move from right to left as we go across the screen. So we'll start with some that look like this. Okay, now on this one, I think I'll back it up and actually put it about right here just so it doesn't get confusing. Okay, let's take a look at this one. Now this is basically, again, just a parabola that's been turned upside down, and I want a rough sketch of this without going through a whole lot of detail on this. Now what I would suggest you guys always do is take care of the horizontal tangent lines first. So what I'm going to do is wherever I have a horizontal tangent, and I'll draw a line right across here, there's a horizontal tangent. That means that the slope is equal to 0. So from this point right here, comes straight down like this to here, and that means that the graph of the derivative has to cross the x-axis right there. Now, as far as detail goes, all we care about is this. That divides it kind of up into two intervals. We'll think of it like this. In this interval over here, all the slopes are positive. And they start out, this might be, just to give it some numbers, this might be like a positive 8. Then it goes to a positive 6. Then it goes to a positive 4 maybe. Then a positive 2. So what that means is the graph of the derivative is going to be above the x-axis. So it'll be positive. It'll look like this. Then in this interval, wherever you pick a tangent line, this would be maybe a negative 2. This might be a negative 4. This might be a negative 6. But they're all negative, which means that the graph of the derivative is going to be below the x-axis. It'll look something like that. And the graph of the derivative would look something along that line right there. So just a rough sketch. Now let's take exactly the same graph and just shift it over a little bit. So rather than having the vertex be up here, let's put it down here, but you'll see the same idea. Now once again, when you're going to sketch the derivative graph, the first thing to do is draw yourself a horizontal tangent. So the horizontal tangent goes right there. Now the slope of that line is 0. So from that point comes straight down, and that means that the derivative has to go through the x-axis right there. Now once again, all the slopes over here are positive, so it's above the x-axis, and it starts out here maybe a positive 10, a positive 8. So it's going to be positive, and it's going to look something like this right here. It goes off like that because all of them are positive above the x-axis. In this interval, you might have maybe a negative 2, a negative 4, a negative 6, and so on. But these are all negative slopes, so it'll be below the x-axis. It will look like that, with negatives on this side. So again, on these two graphs, wherever you have a horizontal tangent, the derivative graph goes through 0. If the slope of the original function is positive, then the derivative graph is above the x-axis. If it's negative, it's below the x-axis. And we're not going to worry about whether it curves a little bit or a straight line at this point. We just want a rough graph. So let's take a look at a couple more examples. Okay, let's try these two right here. Now, first of all, again, take care of the horizontal tangent lines first. So I'll come in here and I'll draw a horizontal tangent line here. That's where the slope is equal to 0. So it comes straight down from that point, and that means that the derivative graph has to go through 0 right there. I've got a horizontal tangent line right here. That's where the slope is equal to 0. Comes straight down from that point, put a point on the x-axis right there. So the derivative graph has to cross the x-axis at those 2 points. Now you want to know, is it above or below the axis? Well, to figure out whether it's above or below the axis, just look at the original graph, and again, you can kind of divide it up into intervals here. You've got an interval from here and here. In this interval over here, all these slopes are positive. So the derivative graph will be above the x-axis. It'll come in something like this. Then in this interval, all the slopes in here, wherever you draw a tangent line, no matter where you draw it, it's got a negative slope, so this is going to go below the axis. It'll go down something like this. So it'll be positive over here above the axis, it'll be negative in here. Then it levels out at 0. Then back over here again, all your tangent lines are positive, and they're getting increasingly steep, so it would go up something like this, and you're done. There's a graph. Now, one thing some students have trouble with, they want to know, well, how do you know whether or not, how far down to make this part right in here? So let me erase that, and then we'll try it again. So the question is, should it look like this? Or maybe should it go down this far? Or should it go down this far? How do you know how far down it goes? Well, let's go back and we'll take a quick look at that, and we'll just erase these parts right in here. And let's try that one more time. So if you want a little bit more detail, what you can do is this, is just go to the steepest part of the graph in that interval, which is about right here. So find the steepest point on that graph and draw yourself a tangent line. Now that's actually called an inflection point, but if you were to take the time to find the slope of that line, let's just suppose it turned out to be a -2. At that point, if the steepest slope is a -2, then from that point go straight down and go to a -2, about right there, and you can actually kind of sketch your curve where it goes through, something like that. So again, to figure out how far down it goes, the farthest down it will go is whatever the steepest value of the slope is at this point right here. So with that in mind, we'll try a couple more. Now again, where the original function is positive, it's above the axis. Where it's negative in this interval, it's below the axis, and where it goes back to positive again, then this one goes back above the axis. So let's try this one. Okay, first thing, horizontal tangent. So the slope is equal to 0. So it comes straight down from that point and crosses the x-axis right there. Next one, got a horizontal tangent right here. So the slope is equal to 0. And since the derivative is the slope of the tangent line, comes straight down from here, put a point right here. Now you got to figure out, is it above or below the axis in that interval? Well, pick just any point and we'll sort of divide it up into intervals up here. This one and this one. So first of all, looking at this first interval over here, if you pick any point, all those have a negative slope. And they start out pretty steeply negative, like -8, -6, -4. So since all those slopes are negative, it's going to be below the axis. It'll come up something like this, with a little arrow going this way. So negative is below the axis. Okay, in this interval, now pick any point you want, draw a tangent line. All these slopes are positive. And they will hit a peak wherever the steepest value of the slope is. I'll say it's right about there, and that looks like a slope of maybe 1.5. So at that point, I'll go up to 1.5 and put a little point about right there. It's going to go above the axis and go something like that right there. So all the slopes in here are positive. This derivative graph is going to be above the axis. And then finally, when you cross over here, now all the slopes here are negative again, maybe at -2 and -4 and so on. So this one will drop back below the axis and they'll all be negative over here, and that's what the graph of the derivative is going to look like. All right, we'll try a few more and just continue this idea. Let's go with just this one right here. Now this one has 3 horizontal tangents. So I've got a horizontal tangent right here. I'll go straight down from here, and it has to go through the x-axis right there. Got a horizontal tangent right here. Goes straight down. It has to go through the x-axis right there. Horizontal tangent right here. Goes straight down. It has to go through the x-axis right here. Now, in this interval, it's got and again, we'll sort of divide it up. It may help you to put a little interval division up in here like this. So something like that. So in this interval over here, the slope, no matter where you draw a tangent line, is positive. So this one's going to be above the axis, positive. Anywhere in here is going to have a negative slope, and you might estimate maybe the maximum negative looks like it might be about a -4, 3, something like that. So we'll go down quite a bit negative here. It's going to be negative below the axis in this interval. In this interval, no matter where you pick a tangent line, it's always positive. So you've got positive slopes in this interval. So it goes back above the axis. And then finally in this interval, everything is negative. So it goes below the axis. And the graph of the derivative would look something like that. So wherever the original function is increasing, the derivative is above the axis. Wherever the original function is decreasing, it's below the axis. Now in this case, these were just rough sketches with general curves. If you have straight lines, you can put a little bit more detail into it. So let's take a look at those. And we'll do a couple of straight line ones here. Okay, now this is a little bit different. What we'll do on this one is, again, the same rule holds. Wherever you have a horizontal tangent, the derivative is 0. So from here to here, the slope in that entire interval is 0, so that means that the derivative graph is 0 in that interval, from here to here. Now you might remember from your earlier descriptions of derivatives, wherever the original graph comes to a sharp point, the derivative is undefined. So the derivative is going to be undefined at this point and this point, which means you're going to have an open interval right here. So an open interval there and an open interval there. Now for this part, another rule. Wherever the original graph is a straight line, then the derivative graph is going to be a constant because the slope here is the same as the slope here is the same as the slope here. So you can pick any point in this case and actually find the slope. So let's go from here to here. It goes over 1 and up 2. So the slope of that line right there is 2. So that means in this interval, the derivative graph has a value of 2, so it's a horizontal line that goes right through 2. It'll have an open point there, and it goes on. We're assuming that this thing goes on forever, here and here. Okay, now in this interval, again, it's a straight line, so it's also going to be a constant. Now, this one had a positive slope, so it's above the x-axis. On this one, you go over 1 and down 1, so the slope is a -1. So in that case, this is going to have a slope of a -1, which would look like this, and it'll be open right there. So the derivative graph consists of 3 straight lines, all of which are horizontal. So wherever the original graph is a straight line, then the derivative graph is going to be horizontal. If the slope of the original graph is 0, then the graph of the derivative is 0. Let's try this one. Now, in this interval right here, the slope of that line is horizontal, so the derivative, and that means that the slope is 0, so the derivative graph goes right through 0 to right there. Then, in this interval, let's find the slope. You go over 1 and down 2, so over 1, down 2. In this interval, the slope would be a -2. So we'll go to -2. It'll be a straight line because it's a constant slope till it gets to right there. Then in this interval, again, the slope is a horizontal line. The slope is equal to 0. So it goes back up to 0, and this graph of the derivative would be 0. So that's what the thing looks like. So again, if the original graph consists of straight lines, the derivative graph will consist of horizontal lines. Let's take a look at a couple more. Let's take a look at this one. And one more time, in this interval, it's going down, and I'll just kind of pick a couple points here. From here to here, it goes over 1 and down 4. So the slope right here is a -4. So that means in this interval, down 1, 2, 3, 4, it's going to look like this. And it'll have... And again, wherever you have a sharp point, the derivative doesn't exist. Then in this interval, over 1, up 1, so the slope right here is 1, so it'll go up to 1, and you'll have a line that looks like that with an open interval. So the derivative graph is just the slope of the original graph. In this interval, you go over 3 and down 1. So the slope in this interval would be a -1/3. So we'll go to a -1/3 and just kind of estimate that, which would be about right here. And it goes over to here. And then finally in this last interval, it goes over 1 and up 1. So the slope in this last interval is 1. So it jumps up to 1 and goes across, and we'll assume that it goes on forever. We'll assume both those went forever in that direction. Okay, a couple more. Let's take a look at a couple of graphs that are either constantly increasing or constantly decreasing. Now in this one, if you wanted to, you can again pick a couple points here. What I'll do is just pick one. Tangent line right here, it's got a positive slope. 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 And it's got a positive slope. Now, if it helps you, you can kind of think of some number values on these. Maybe the slope of the tangent line right here might be 1. The slope of the tangent line here might be 2. The slope here is 4. The slope here is maybe 6. Slope here is maybe 10. And you can kind of plot those points. So it comes across, say, at a 1, a 2, a 4, a 6, and a 10 goes up like this. And if you completed the graph would look something like this. So if the original function is constantly increasing, then the graph of the derivative would be constantly increasing. And if you want a few specific points, just pick a few specific tangent points on there and estimate the slope of the tangent line at those points. Let's try one where it's constantly decreasing and do the same thing. It's just if you pick a few specific points, that's got a negative slope. That one's got a negative slope, and it's a little bit steeper. That one's got a negative slope. That one's got a negative slope. But they continue to get steeper and steeper. So it starts out with a shallow negative slope, and then as you go across, they become more and more and more negative. So again, the graph of the derivative follows the same general shape as the graph of the original, except that this time they're all, on this graph, they all have positive slopes, so they were above the axis. On this one, all of these slopes are negative, so this graph is below the axis. So there's a couple of constantly increasing or constantly decreasing ones. A couple more. Let's take a look at some with asymptotes. Okay, now we sort of play the same game here. If the original function has an asymptote, then the graph of the derivative will have an asymptote of the same thing. So if you want to start with, you can go ahead and stick an asymptote right in here. Now to figure out what's going on. In this one, the slope, no matter where you pick a tangent point over here, the slope of the tangent line is positive, and it's getting increasingly positive. So again, maybe 2, 4, 6, 8, 10. So this one's going to start out above the x-axis and go like that. So all these slopes were positive, so all these are above the x-axis. Now on this one, if you wanted to, let's just kind of pick a few. I'll pick this one. Suppose this is about a negative 10. I'll pick a tangent line here. The slope of that one's about a negative 8. Pick one here. Slope there is about a negative 6. Pick this one. Maybe the slope here is about a negative 2. So this one's going to start out at a negative 10. Now they're all going to be negative, but it's going to start shallowing out and approaching 0 as it comes up. So if you plotted these specific points, it would look like this. All these would be negative. So again, since all the slopes of the tangent line in this interval are negative, this one is below the axis, so the derivative graph looks like that. Now let's compare that to this one right here. Again, where you have an asymptote, you can go ahead and put an asymptote on the derivative graph. Now, just like this one was, this one's going to be exactly the same thing. All these slopes are positive, and they're becoming increasingly positive. So this one's going to come in like this and curve up like this. Now, it's a little different on this side, though. Look at what happens over here. Over here, all these slopes were negative, but now I kind of play the same game. Slope right there might be a positive 10. Slope right here might be a positive 8. Slope right here might be a positive 6, and so on. Slope right here might be a positive 2. So this one's going to be positive. It's going to start out kind of steep, and it's going to shallow out and look something like that right there, approach the x-axis. So again, just since all these slopes were positive, it's above the x-axis. Since all these slopes are also positive, it's also above the x-axis. Let's take a look at a couple more. Okay, now we do exactly the same thing. Here's an asymptote. So the first thing I do is the derivative will also have an asymptote, where the original one does. Now again, at this point, this is a negative. Let's just give it maybe a negative 2. This one's going to be a negative, maybe a negative 4. This might be a negative 8. This might be a negative 12. So they're going to start out negative, and they're going to continue to get more and more negative, more steeply negative as it goes. So it's going to look something like that. So since all these slopes were negative, this one is below the axis. Now on this side, just pick a few points. Slope right there might be a positive 10. Slope right here might be a positive 8. Slope right here might be a positive 4. Slope right here might be a positive 2. So this one's going to start out at a positive value and begin to shallow out towards 0 as it comes in like this. So that's what that one's going to look like. So again, all these slopes were positive, so this one is above the axis. And one more just to count all the possibilities. Again, there's an asymptote, so we'll put an asymptote in right here. This one, the slope right there might be, just pick some numbers, say a -2. This one might be about a -4. This one might be about a -6. The slope of this might be about a -10. So if it helps you, just get some numbers. So it starts out with some low negative numbers, and then the slope begins to increase as you go this way and increase negatively. So it'll turn and go like that. So the values of the slopes here are all negative. This one is below the axis. Now do the same thing over here. I'll pick some points here. Just make a guess. I'm going to say that's a -10. I'll say this slope right here is about a -6. I'll say this slope right here is about a -2. They're all negative. This one might be a -1. So I start out with some big negative numbers, and as I go this way, they start shallowing out. It winds up looking like that and looks like this. So all of these slopes were negative, so this one is below the x-axis. And I believe that's our last one, and that's it. So there's some samples for you, but just remember, when you're sketching graphs, I think I'll go back to these two right here, just to remind you, wherever, if the original graph is a straight line, then the graph of the derivative is going to be a constant. And then if you're sketching curves, we'll kind of use this as an example, wherever you have a horizontal tangent, you can come straight down from that horizontal tangent, and the graph of the derivative goes right through the x-axis. Then it's just a matter of trying to figure out, well, if the slope is negative, it's below the axis. If the slope is positive, it's above the axis, and back to negative, it's below the axis. So anyway, that's a quick way of doing curve sketching without a lot of detail, but enough just to get an idea of what the shape of the derivative graph looks like.